All right, so thank you for attending our talk. So we would like to present with my colleague Gabriele. My name is Julien. We would like to present a technology on which we've been working for a bit more than the past year. And it's called Zenoh-Flow. It's based on Zenoh. If you have attended the talk earlier this morning about Zenoh, so this is built on top of Zenoh. And so what we want to do with this is to create something data flow programming. And so in order to assess its capabilities and to show how well it can do, we wanted to have a kind of a fancy use case. So we are definitely not we are not intending on the SDV market. We're just trying to improve this autonomous driving pipeline for showcase. So first off, what is Zenoh-Flow? So Zenoh-Flow is data flow programming for cloud-to-thing applications. So cloud-to-thing applications, the idea is to be able to target things that go from the microcontrollers up to the cloud and in between the edge. So for that, we provide a unified abstraction, meaning that no matter where you want to deploy your application, you should have exactly the same abstraction. No need to use a different framework, no need to use a different language. It's Zenoh-Flow. We want to automate and make the deployment location transparent. So what that means is you, as a developer, you don't have to know where your nodes, where your components are going to be deployed. We're going to do that for you based on a set of requirements and tags. So we build that technology just like Zenoh on Rust. So we want that for high performance. We can do zero-copy communications and even optimize communications depending on where your data flow is deployed. And we want low latency. So let me put that with an image. So this is a data flow, very basic. You have your application is decomposed into nodes. And as you can see, the arrows, they signal the data dependencies between the different nodes. So these work very well inside a single runtime. And so we want Zenoh-Flow to both address this, so your application is running on a single device, but at the same time, we want to be able to target the cloud-to-thing. So if we imagine now that your application runs, few parts run on the thing, so that could be a robot, that could be anything that is low, let's say, then you want to process, send part of this data to the edge. So let's say, for instance, you are in a farm and you have your tractor and you're moving, and so your tractor doesn't have any computing power. So you need to send the processing to move part of the processing up to the edge. So this is this. And then maybe you want to send data to the cloud. So for later analysis or maybe to run heavy, intensive computation. So this is what Zenoh-Flow tries to address. So all of that is made possible thanks to Zenoh. So Zenoh was introduced earlier this morning. So basically it says, tries to unify data in motion, data at rest, and computation. So data in motion is a fancy word to say that, okay, we move the data for you while it's being computed over. Data at rest is to say, okay, you have storages, and so you're both able to target this, get this data that is moving, and also maybe you want to store it and retrieve it later. This is data at rest. So it provides a location transparent API, meaning that you don't need to know where the data is located. You just need to know its resource key, and you can access it no matter where it is. Zenoh will take care of routing it and fetching it for you. All right. So as I mentioned earlier, so the motivation for this talk is, okay, we built Zenoh-Flow is novel. We built it to be better. Now, okay, can we prove it? And so the idea was to tackle something that is a bit intense in order to prove that we can do it. So we took Pylot. So Pylot is an autonomous driving pipeline developed by Berkeley. It provides state-of-the-art reference implementation for the components. So here there would be the perception, the prediction, and the planning. So what we did is that we took these components, and underneath Pylot there is a framework called RDosh. And so we removed RDosh and put Zenoh-Flow instead. Why? So as I said, autonomous vehicle is a kind of a sexy use case nowadays. So it's also complex. So we have lots of sensors, we have different nodes running, and we have high throughput. So this high throughput is because we're sending images, and so we're sending images regularly. So this is the difference between the perfect pipeline and the AI is the fact that perfect pipeline is getting information directly from the simulator. So Pylot is running on a simulator called Koala, whereas the AI will get the images from the simulator and then try to assess, to guess the information based on these images. All right. So why should you be interested? So we feel that with the rise of 5G and IoT, we're going to have more and more complex applications, more and more applications that go from microcontrollers up to clouds. And so we feel there is a need to make them easier to deploy, to make them more robust, more structured. And we feel like Zenoh-Flow answers these challenges. Okay, so how exactly is Zenoh-Flow? How does it work? So first, as I mentioned, it's a unified abstraction inspired by data flow programming. So basically, your building blocks are nodes that receive inputs and produce outputs. A computation in Zenoh-Flow is deterministic, meaning for a same set of outputs, you produce the same set of inputs, you produce the same set of outputs. We ensure this by adding timestamps to every data that's produced, such that you can record them, you can then send them again. We will be able to send them with exactly the same time lapse between them, such that you will have the same output. This set of abstractions is viable from MCU to cloud server. Now we offer multiple bindings, so we have bindings in Rust and Python. C++ bindings is coming. The interface is quite straightforward. Zenoh-Flow is declarative, so this is something that we feel is important. As an application developer, you need to know what is happening. And so for that, we ask you to describe your application with a description. This is YAML. And so the idea is to show us, okay, so that flow has one operator, a source that will capture data from a camera, and a sink, so which will digest the data. And so these are the links between these. So we see that, and for Zenoh-Flow, this is a contract. As in, this is exactly what's going to deploy. So we feel this is important because there are other frameworks, for instance, in robotics, where all nodes publish to every other nodes in the system. So you can be flooded, you can have collisions between these publications, and this is messy. So we want to avoid that through a declaration that we enforce. Zenoh-Flow is performant. So low latency, optimized communications. So this, I want to insist a bit, optimized communication, the idea is Zenoh-Flow, based on the deployment you give us, will know when two nodes are running on the same machine. And so what we do is that we won't send it over anything. It's just going through channels. So this is how we achieve this super low latency, or microseconds. It's a channel between two nodes. High throughput, so this has been measured on our test bed, a little bit more than 1,600,000 messages per second with a payload of 8 bits. All right. Last is automated deployment. So as a developer, you have everything on your infrastructure. Okay, we don't want you to have to log to SSH into each device and start each node at the correct order. We want to do that for you. So Zenoh-Flow, a daemon, is able to automatically manage the life cycle of nodes. So which one to start, where to start it, how to start it. So I have a small, before an example, I have features that we support. So right now we support loops, the definition of loops in the data flow. We support deadlines, so I put a little star here because it's not what we want to do is that for you to define it in the YAML file, you can say, okay, that node has to run under 50 milliseconds. It's not yet there in the YAML file, but you can define it in your node. You can put the logic yourself in order to have the deadline. So we support it. We support composite operators. So for instance, if you have AI, that is the several nodes that each does a specific step, you can define it in an outside YAML description. That will be a new operator. And then in another flow that uses exactly the same, you just need to import this composite node. We support callbacks, so the idea is you can tell us, okay, trigger that whenever I receive information. Asynchronous user code, we have a command line tool and data isolation. So for instance, if you run several times the same data flow, we will make it so that there is no data collision. We will ensure that each flow receives just its data. So what's planned? So a registry. So the idea would be you develop your node, and maybe you want your colleagues to benefit from what you've developed. And so we are implementing right now a registry where you would be able to put the result, shared library, on that registry that Zenoh-Flow will then be able to fetch and automatically load for you. Tag-based mapping. So I will come up next. I show you an example of a deployment that's driven for now by you specifying where you want to put your node. So tag-based mapping would be you specify on your daemon what are the capabilities it has. You specify in your description what are the requirements for your nodes, and we do a match with this. Graphical interface to create the YAML file for you, so C++ bindings and ROS2 integration. All right, lots of information. So how does it work? How do we deploy a data flow in Zenoh-Flow? So let's assume this is your infrastructure. So you have a robot here on which there is a Zenoh-Flow daemon. You have a router here on which there is Zeno and a Xenoflow plugin. You have several other routers, and here you have a storage, and this is your cloud where you have most computing resources. So you, as a user, you will describe your flow here, and you will communicate with a Xenoflow, a Zeno router that is able to automatically detect the Xenoflow daemons on your infrastructure. What it will do is that it will select this daemon and, okay, ask it to instantiate the flow. So for that, we store it thanks to Zeno in the storage, and then this router will orchestrate the deployment. It will ask all the daemons that are involved in the flow to go fetch from the database the YAML, the description, so that way they know what to deploy, and then you run your flow, and that's it. So as a developer, what you needed to do is just describe, and then Zenoh-Flow will be able to deploy everything for you with an orchestrator. All right. So that's the first part. So this is Zenoh-Flow, our objective, how it works, a little bit of a deployment. So now, the purpose of the talk, Zenoh-Flow Drift.
The fun part. So thank you, Julien. Can you give me? Yep. Yes. So as Julien mentioned, so the goal was to verify that Zenoh-Flow was able to cope with some use case that was not just sending some bytes here and there, but also where we have some time constraints. So what we did was to define a graph that is a little bit more complex than something that's simple. This case is a graph that is used with the perfect perceptions, getting data from the ground truth of the simulator, is computing something, and then producing something to, at the end, move the car. So as we can see in this graph, we have different components. This triangle on the to the right, are the ones that are used to get data out from the simulator, but they can also be seen as source of data in general, so they can be sensors directly in the car or that kind of things. Then we have different components, the operators, the ones that are circles, that are computing over those data, and they're producing some results that then is by other components. So we can see this guy is doing some localization based on information from the ground truth, while this is doing some tracking, and this is doing some time to decision, and so on and so on. And at the end, we have a sync that is something that's interacting again with the external world. In this case, it's something that is sending to the simulator where the car has to go. So what we have done, we take one simulator, that is the Carla simulator, is a well-known simulator for autonomous vehicles, was made by the DARPA for the DARPA challenge about autonomous driving. So it provides a different set of scenarios, different sets of maps, and different set of vehicles. So what you do, usually you configure the simulator to give you a specific city with a specific scenario, specific cars, and so on and so on. And then you attach sensors to the car. So in this case, for this specific demo, we attach 2 cameras to the car, one in the front bumper that is used to for close detection, and one that is like a kind of call it tele camera, so it's able to look more in the distance. And then we attach also their sensor like IMU, GNSS, and so on and so on. Then once the car is there and the car is running, so once the simulator is configured, we spawn Zenoh-Flow, and we tell to Zenoh-Flow to run this precise flow. So Zenoh-Flow will load all the different operators, will connect to the simulator, and will be able to drive the car. And yes, okay, it's able to drive the car, but in the description of the talk, we said that we improved something. What does it mean? That we run some tests. So we go through 3 different scenarios. The 3 different scenarios are about like, you have an intersection in which you have the green light while the other car has a red light but decides to run the red light. So you need to discover that there is a car that is running off a red light. You need to stop, which is this scenario. Another scenario is about you are going to turn right and there is a pedestrian crossing. So you have a green light, you are turning right, but there is still a pedestrian, and that's the priority, so you need to avoid the obstacle. Another one that is about lane change. So as we can see in those graphs, what we think we really improved is the fact that, as we can see, the simulation time is the same, which means the pipeline took always the same time to run the scenario, but the system time is significantly lower, which means that Zenoh-Flow was able to cope more with the requirements that come from the autonomous driving, which means for running that amount of time, the simulation that ran around in this case is around 100 seconds. We took a little bit more than 250 seconds.
Yeah, so this is the version 0.3, so we are a recent project, so we're already about to ship version 0.4, and the performance are even significantly better.
In this case, we were not using the perfect perception, because the perfect perception is easy. You don't have any AI and so on. In this case, we were really using the AI and way more sensor that they were in the perfect perception. So that's why the simulation time is not exactly equal to the system time. So our goal is that once we have, our goal is to improve also a little bit more the full pipeline to be able to show that we can have simulation time as close as possible to the system time. So we have a small video about this. I need to press enter, right? Yes. So this is the image captured by the camera. In this case, this is the bumper camera, and we are just driving the car. I will change in some seconds from one camera to the other camera, just to see that we have actually 2 cameras. Yes. So, okay. Quality is not that good, but okay. And so this is done using the perfect perception. So we see that the car is able to drive at real time. If we happen that we change this pipeline with the AI, it will be way slower. But just because Pylot per se is written in Python, that is not perfect for performances, and plus is using different kind of AIs that are used for all the discovery plus the LiDAR and so on and so on. So this will slow down the whole simulation. There is also a problem that comes from this simulator that is as long as you start adding more and more sensor, each sensor will slow down the simulation itself. So let's imagine, in this case, we had just 2 cameras and the simulation was smooth. If we start to add 2 cameras, 2 different LiDARs, and more sensors, the simulator will not be able to generate the data in time. So because this simulator is not only generating, let's say, the 3D view, because that's easy. Every 3D game, modern 3D game can do things even better. But the problem is generating, for instance, the reading from a LiDAR, because he has to generate the laser scan, so compute all the points. So that's why for the demos, we use the pipeline with the perfect perception, because that's really show that, okay, Zenoh-Flow is able to cope to sending this data across the full pipeline, and is not slowed down by anything else that is not Zenoh-Flow. Well, that's something that we have to say. So this project is founded by a European project, which is Demon, which is about network intelligence, in which we are using also Zenoh-Flow to deploy some of the network intelligence. Thank you. Any question? Yes, please.
No, thank you so much. I think such as autonomous driving application, like a critical application, is the deterministic behavior is very important. So my question is, do Zenoh's objective include such as guaranteeing the deterministic behavior?
So for all the data flow is created, we have deterministic behavior in the sense that if your operator is purely functional, we will given the same set of inputs, we will always produce the same set of outputs. We are able to record the inputs, which means that, for instance, if we go back to where it was, no, this one. If we, for instance, let's imagine we record the information about the current position of the car. We are able to record them and to timestamp them with using hybrid logic clock plus unique IDs. So we get total ordering of the data that is going through the flow. And this means that if, for instance, this operator this one is purely functional, so it has not state, it has any state, is we are able to do determinism.
Thank you so much. How about the execution time perspective?
So on that is something we are working on, because for the time being, the whole project is written in Rust and leverages AsyncSD, which is a Rust library for asynchronous programming. Mm-hmm. And from what we have seen is quite good, but for instance, we cannot tell to AsyncSD when we spawn a task the priority, which in this case of things, in this case is very important, because let's imagine we have something like, let's imagine the controller that is the one at the end, is a PED that at the end is sending to the car what to do. Maybe we want him to always produce a kind of output, even if the other one are not. And in this case, the output will stop the car because we didn't manage to do the things. For the time being, we are not able to do so because we rely on AsyncSD that, as I said, it does not allow us to do that kind of things. So in the future, what we plan is to study more in depth all this problem and see if we can come with our runtime for asynchronous task that could take care of these things.
Just one precision. So this is an example use case. And so obviously an autonomous driving pipeline has time constraint, real hard time constraints. This is not per se the objective of Zenoh-Flow. It's one application that we can do. Well, we can do a simulator that we can do. But it was to demonstrate the potential of Zenoh-Flow. So right now, we're at the stage where we are quite happy about where we're going. We're quite happy with what we have. And so this is an illustration. But we feel the Rust ecosystem in particular might not be yet ready for this, for instance, because of certification issues and compliance and real-time constraint with the AsyncSD. So ecosystem is not yet there, but this is just an example. We do not guarantee that we will do real-time constraints. We hope.
Thank you.
Any other question? Well,
thank you.
Well, thank you very much. I think we're a bit early, but if you have any questions, we're here. Feel free to come talk to us.